All right, back for our last part of wave phenomenon, interference, and we get to talk about the most interesting part, standing waves. If you go on and take AP, we spend a lot of time talking about standing waves because they're very, very interesting. They have applications well beyond what we even get into in AP. Very, very cool. So, a standing wave is a special type of wave that involves two waves interfering. These waves have to have equal amplitudes and equal frequencies, and they have to be traveling in opposite directions. When they interfere, they produce this effect, and it is called a standing wave. And it's called a standing wave because, unlike most of the waves that you see, and you can tell which way they're moving, standing waves just seem like they stay in place, okay? The pattern of interference, constructive and destructive, is such that it doesn't look like the wave moves to one side or another. So, this is a picture, this is kind of different like snapshots of two waves that are moving in different directions, same amplitude, same frequency. Okay? You can tell because they have the same wavelength, they have the same frequency. Well, I guess we don't know what this axis is. They have the same amplitude. You can tell when they're perfectly overlapped. This, again, is called maximum constructive interference. We get this blue line that is much, much bigger. But as those two waves start to separate, that blue line decreases in height because now the waves aren't perfectly lined up. And then later on, we get some destructive interference when the waves are mostly canceling each other out. Now, this is very boring to look at when you're talking just pictures. So, let me show you the little app here. Okay, so you guys have seen this before. We've got our blue, I've used this either in class or on another set of videos. We've got a blue wave, and the blue wave is traveling to the right. I've got it moving in real time. Now, also, I could turn off this blue wave for a second, and I've got an orange wave that's traveling right to left. And that orange wave has the same amplitude as the blue wave, and they have the same frequency. So something interesting is going on here. We've got two waves, same amplitude, same frequency, traveling in opposite directions. If I turn them both on at once, okay, well that's not the standing wave yet, because the standing wave happens when we combine their two effects. This is just a trippy picture. Let me slow it down so you can still see that everything is still functioning the same way it was before. Here's a blue crest traveling this way. Here's an orange crest. They overlap, and now they're moving this way. Now watch what happens when I turn on the combined wave, the superposed wave, this green wave. This is really neat. Okay? The green wave is what you would be seeing. Notice when the green wave has a maximum height right there when they're overlapped. And then when they're overlapped again. And when it cancels out, if you look, you have orange crest, blue trough right on top of each other. Blue crest, orange trough right on top of each other. We get maximum destructive interference. So I'm going to put this back into slow motion. I'm going to hide my two waves. This is what you would be seeing, okay? This is what you would see in real time. Does it look like this wave moves left or right? Not at all. Okay? It seems like it just oscillates or stands in place. That's all it does. This is what a standing wave is called. This is what it does, okay? Now, if it's moving real fast, I wish it was moving even faster than this. If it was moving even really, really fast, you wouldn't even be able to tell that it's going from one to the other. What it would look like is just almost like a loop, okay? It would look like an open loop that you would see. Almost like the string or whatever is in two different places at once. As a matter of fact, I should have looked this up beforehand. Let's see. Standing wave string. Okay, here we go. So hopefully you can see what's happening up here on the board. But he has a wave that is oscillating so quick. Doesn't it look like there's more than one string up there? It looks like there's like two loops up here. Allegedly, I have one of these machines that can do this somewhere in the room. I have never found it. I haven't ever actually found it. Would love to find it. Anyways, that's what a standing wave does. The standing wave, as you can tell from our app, it oscillates between basically two different positions. It oscillates between a peak here and a trough here. And it just goes back and forth. Okay? So, we have names for these locations. No, that's not what I want. It's essentially oscillating between these two parts, right? We got a peak here, trough here, peak, trough, peak, trough. Any location where the full line and the dotted line meet is a point that really doesn't move at all. If you look on our app, let's see here, should I turn these on? No, it's more confusing that way. Let's just put the green one on. But there are locations here, 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 here. You get the picture. All these locations, look, the wavelength isn't even moving at this point. Okay? That's because at those points, if I turn those off, at those points, there is always maximum destructive interference. Take this for example. Okay? Look where the orange and the blue are. They're always exactly opposite. Okay? These points are special. They have a certain name. Okay? These points are called nodes. N-O-D-E-S. The reason that they never seem, like the wave doesn't ever seem to have any height there, is because at that location there is permanent maximum destructive interference. And again, that is called a node. On the other hand, there are locations, and I won't go back to the app for this one, but away from the nodes, I'll say like right here, or here, or here. And I'm not talking about these actual locations, I'm talking about like this whole plane right here, and this whole plane, and that whole plane. There are locations where the peaks, okay, where the highest points happen. All right? And that's due to maximum constructive interference. Now, if this and this and this and this were called nodes, then not very creatively, these points right here that I have marked right now, they're referred to as antinodes, okay? They're, I guess, what you could call like the maximum, like the locations where you get the maximum height because of constructive interference. In other words, it's kind of like the loops, okay? The highest point on these loops. These are referred to as antinodes, okay? So, standing waves are important, especially if you're into music, because every single musical instrument has at its core, the reason that it works is due to standing waves, okay? They have really interesting effects if they're allowed to persist for a long period of time. Reason being, every object has what's known as a natural frequency. This is just a frequency that the object will naturally vibrate at if given the chance, okay? A certain frequency, a certain number of cycles per second. Okay? Different materials have different natural frequencies. If a wave with the same natural frequency as the natural frequency of the material interacts with it, what happens is it causes the object to vibrate at its natural frequency. And we're going to talk more about this when we get to sound waves, which is coming next. But there's a lot of interesting ways that this can happen. And this is generally known as resonance, okay? When you get a sound wave, or when you get any wave interacting with an object that has the same natural frequency, it'll cause that object to start vibrating, even if that object wasn't hit by anything. It's hit by nothing but the wave, and it starts vibrating. That is known as resonance. And resonance is the principle behind every single musical instrument. If you didn't have resonance working for those, even those big instruments that are really, really loud, trumpet, saxophone, all those, the reason they're so loud is because they resonate very well. They're designed to amplify those waves. When you get something undergoing resonance, what essentially happens is the volume gets kicked up like 10 notches. Okay? It allows the volume to increase. Resonance is also the phenomenon, like I said, we'll talk about this a lot more in the next section. Resonance is also the phenomenon that allows an opera singer, hopefully you ever seen kind of heard the story, like an opera singer, they're singing at the glass, and they're singing at such a pitch that they cause the molecules in the glass to vibrate back and forth, and they shatter the glass with nothing but their voice. That's a real thing. That can actually happen. Okay, it's kind of rare, but it is possible to do. Okay? Mainly what I want you to get out of this is that standing waves happen when you have two waves traveling opposite directions, same frequency, same amplitude. You should be able to tell what is a node and what is an antinode. You should know the reason that they're called standing waves. Like I said, we'll talk a little bit more about resonance. Every once in a while in the readings, there is a question asking about resonance, and mostly it's just an identify what this is sort of question. Like, why are these waves being amplified so much? Oh, it's because of resonance. Good, there you go. Okay, so that does it for our first part of the waves unit. So that's really good. And we'll be back for round 2 later on.